Nanoparticles are tiny particles, generally ranging from 1 to 100 nanometer, in at least one dimension. Their incredibly small size gives them unique physical, chemical, and biological properties that differ significantly from their bulk counterparts. These distinct properties make them valuable in a wide array of applications across various fields. Structure. The structure of nanoparticles varies greatly depending on their composition and intended function. Some common structural features and forms include high surface area to volume ratio. This is a defining characteristic of nanoparticles. As the size of a material decreases to the nanoscale, the proportion of atoms on its surface relative to the total number of atoms dramatically increases. This high surface area makes nanoparticles highly reactive and provides numerous sites for chemical reactions, adsorption, and interactions with other molecules. Quantum effects. At the nanoscale, quantum mechanical phenomena become dominant, influencing the optical, electrical, and magnetic properties of the particles. For instance, quantum dots exhibit size-dependent light emission, meaning their color changes with their size. Diverse shapes. Nanoparticles can exist in various shapes, including spherical, rod-shaped, hexagonal, tetrahedral, cylindrical, and irregular forms. The shape can significantly impact their properties and how they interact with their environment. Crystalline or amorphous. Nanoparticles can have a well-ordered crystalline structure or an amorphous, disordered arrangement of atoms. Core shell structures. Some nanoparticles are designed with a core of one material surrounded by a shell of another. This allows for tailoring specific properties, such as protecting the core material, enhancing stability, or providing surface functionalization. Particles are broadly classified based on their composition. 1. Carbon-based nanoparticles. These are composed primarily of carbon atoms. Fullerenes. Spherical or cage-like structures, e.g., C60 buckyball. They have unique electronic and mechanical properties. Carbon nanotubes, CNTs, cylindrical nanostructures with exceptional strength, electrical conductivity, and thermal conductivity. They can be single-walled, SWCNTs, or multi-walled, MWCNTs. Graphene. A single layer of carbon atoms arranged in a two-dimensional hexagonal lattice. Known for its extraordinary strength, conductivity, and transparency. 2. Metal nanoparticles, made purely from metals. Gold nanoparticles, ORNs, known for their unique optical properties, e.g., plasmon resonance, resulting in vibrant colors, biocompatibility, and ease of functionalization. Used in diagnostics, drug delivery, and sensing. Silver nanoparticles, ANS, possess strong antimicrobial and antiviral properties, making them useful in medical coatings, textiles, and water purification. Iron oxide nanoparticles, IONPs, often superparamagnetic, used in MRI imaging, drug delivery, and hypothermia for cancer treatment. 3. Ceramic nanoparticles, inorganic, non-metallic materials, often oxides, carbides, carbonates, and phosphates. Titanium dioxide, TO2 phosphates. Titanium dioxide, TO2, and zinc oxide, nanoparticles, used in sunscreens for UV protection and as photocatalysts for environmental remediation. Silica, CO2, nanoparticles, biocompatible and widely used as drug carriers and for imaging. 4. Semiconductor nanoparticles, exhibit properties intermediate between metals and non-metals. Quantum dots, QDs, crystalline semiconductor nanocrystals that emit light at specific wavelengths depending on their size, making them useful in displays, bioimaging, and solar cells. Examples include cadmium selenide, CDs, and zinc sulfide. 5. Polymeric nanoparticles, organic-based nanoparticles made from polymers. They can be nanospheres, solid matrix-like structures where the active substance is dispersed throughout. Nanocapsules, core shell structures with an active substance encapsulated within a polymeric shell. Dendrimers, highly branched, tree-like polymeric structures with precise and controllable architecture. Liposomes, spherical vesicles composed of lipid bilayers, mimicking cell membranes, used for drug delivery. Solid lipid nanoparticles, SLNs, and nanostructured lipid carriers, NLCs, solid lipid-based systems used for drug delivery. The functions of nanoparticles are incredibly diverse and stem directly from their unique size-dependent properties. Drug delivery and therapeutics. Nanoparticles can encapsulate drugs, protect them from degradation, improve solubility, and deliver them precisely to target cells or tissues, e.g., cancer cells, through passive, enhanced permeability and retention, EPR effect, or active targeting, surface functionalization with ligands. They are used in chemotherapy, gene therapy, and vaccine delivery. Diagnostics and imaging. Fluorescent nanoparticles, like quantum dots, magnetic nanoparticles, and gold nanoparticles are used as contrast agents in various imaging techniques, MRI, CT, optical imaging, and as biosensors for detecting biomolecules, pathogens, and disease markers. Catalysis. Their high surface area and quantum effects enhance the catalytic activity of nanoparticles, leading to more efficient and selective chemical reactions in various industrial processes, including fuel production and environmental remediation. Electronics and energy. Conductive inks. Metal nanoparticles, silver, copper, are used to create conductive inks for flexible electronics. Displays. Quantum dots improve color accuracy and brightness in displays. Solar cells. Nanoparticles enhance light absorption and charge transport, increasing solar cell efficiency. Batteries and supercapacitors. Nanoparticles increase electrode surface area and conductivity, leading to higher capacity and faster charging. Environmental remediation. Nanoparticles can absorb and degrade pollutants, heavy metals, organic contaminants, in water and soil, offering solutions for water purification and environmental cleanup. Materials science. Reinforcement, incorporated into polymers and ceramics to enhance mechanical properties, strength, impact resistance. Coatings, used to create advanced coatings with properties like scratch resistance, UV protection, and self-cleaning. Cosmetics and textiles. Sunscreens, TO2 and ZNO nanoparticles provide transparent UV protection. Functional textiles. Nanoparticles can imbue textiles with antibacterial properties, stain resistance, and enhanced durability. The ability